My name is Babe Mohammed Abdullahi of the Department of Mathematics and Computer Science, Faculty of Science, Federal University of Kashere, Gombe State, Nigeria, Africa. I'm your tutor tonight on a crash course, real analysis, which has to do with analysis of the real line. Here we go. Today we are going to introduce sequence and series. Sequence and series of the real valued function. But before then, we need to introduce functions. Relations, mappings, and functions. In mathematics, for two objects to be connected, we need a box. For two items to be connected, we need a box. That box has a length and breadth, which is A times breadth as the area. This is called Cartesian product of two sets, say A and B. And this is presumed that is a rectangular, which generalizes the concept of the square A cross A, which is A squared. So for sets, for elements of one particular set to be connected, we need another set B that is analogous to A, and this should be tagged as A. So A cross A will now connect A and connect A and B. But set itself without the cross product is not connecting A and B. This is not standing for the box. Now for a relation, we need a smaller box that is a subset of the bigger box. For us to say that two items are mathematically related, they have to be connected. This is the connection and this is the relation. Now we have so many types of relation. We have reflexivity. We have symmetry and transitivity. Two items are said to be related if they can be written in this form. A is related to B. Now, if A is related to A, then we say the relation is reflexive. If A is related to B, implies B is also related to A, the converse, then we say this is symmetry. If A is related to B and B is related to C, implies A is related to C, that's transitivity. Now, a relation that is reflexive, symmetry, and transitive is called an equivalence relation. This equivalent relation used to partition set into disjoint equivalent classes so that each of the class maintain the property of the superset. For example of equivalent relation, we have equality, we have congruent, we have parallel, we have a class made of A is related to A, symmetry. If A is equal to B, then B equal to A. If A equal to B and B equal to C, this will imply A equal to C. So equality is an equivalent relation. Then we have a generalization of equality, which was first introduced by Gauss and Kepler independently, which is congruent. A is congruent to A modulo C. A is congruent to A modulo C means A minus A over C belong to set of integers if we really want to partition set of integers. And this is certainly true because A minus A is 0 over C, which means 0 is in the set of integers. That means 0 is an integer. Now, if we assume that A is congruent related to B modulo C, we want to check out whether B is congruent to A modulo C, means A minus B over C belonging to set of integers. if a number belongs to set of integers, the negative of the number will also belong to set of integers, which means minus a plus b over c belongs to set of integers, which means b minus a over c belongs to set of integers, which means b is congruent to a modulo c. This is reflexive symmetry. Now, for a relation to be reflexive, to be transitive, we need if a is congruent related to b modulo d and b is congruent related to c modulo d, we want to check out if a will be congruent to b, congruent to c modulo d. Now, a is congruent to b modulo c means a minus b over d belongs to set of integers, and b is congruent related to c means b minus c over d belongs to set of integers. An integer plus an integer is an integer because set of integers forms the algebraic structure called ring, which is closed with respect to addition. By taking LCM, we have a minus b plus b minus c. This will go, which is a minus c over d, which means a is congruent related to c modulo d as required. Now, these equivalent classes are partitioning, as we said, set of integers into disjoint equivalent classes. This is the set of integers. Now, to partition this into disjoint equivalent classes, if we want to partition it into 3 disjoint equivalent classes, we use modulo 3. If we want to partition it into 4 equivalent classes, we use modulo 4. Into 5 equivalent classes, we use modulo 5. So, it means A is congruent to B modulo 3, which means A minus B is divisible by 3, belongs to set of integers. So we start with 0 class, which is a minus 0 over 3. Class of 1, a minus 1 over 3. Class of 2, a minus 2 over 3. Now if you check out class of 3, class of 4, class of 5, class of 6, class of 7, class of 8, this is the same thing as this, and this are the same thing as this. So, because of the symmetry, we can also say a minus 0 over 3, 1 minus a over 3, 2 minus a over 3. Now, 0 belongs to set of equivalent class of 0, and 1 belongs to equivalent class of 1, 2 belongs to equivalent class of 2. 3 will be here, 4, 5, 6, 7, 8, and down the line. Now this is partitioning set of integers, and each subpartition maintains the property of the superset. Now if you check out this, if this forms a ring, this will form a subring. In fact, it's an ideal. If this is a group, this is a normal subgroup. Now, we can also decide to partition the 0 class. Now, to partition this, we also need the 0 class Baba and the 1 class Baba. We have 0 here, 3, 6, 9, and down the road. Minus 3, minus 6, minus 9, minus 12, etc. Now, if you check out, this also forms an ideal of the 0 class. Now, it means 0 class over forms a quotient ring by this, or quotient set. This quotient set, if you check out set of integers by the double congruent, the class of 6, this will cancel. It will be nothing but 0 class integer set of integers over the class of 0. This is the third isomorphism theorem. Now, besides partitioning Z with this, we can decide to take the inverse, which is 3 over a minus b belongs to set of integers, which means this is 1 over 1 over with the exception of 0. That's mean minus 0. And this partition will be 1 over, excluding 0, 1 over, 1 over, 1 over, 1 over, 1 over. Now, another thing is we can take the left arm of the set of integers and make the partition. This because of the isomorphism between set of natural numbers and the left arm of the set of integers. Set of integers is nothing but set of natural numbers, union 0, union negative natural numbers. Now, if we define math to this by theta 1, of course, 0 will be mapped to 0. And if we define another math, theta 2, we'll check out that this theta is 1 to 1 and onto, this 1 to 1 and onto, and this is 1 to 1 and onto. Mind you, this is a group. 0 plus 0 equal to 0, closure. 0 plus 0 plus 0 is equal to 0 plus 0 plus 0 associativity. The identity is 0. The inverse of 0 is 0. So this is trivially a group homomorphism. Now, to check out theta of 1 defined by theta 1 of A equal to A is trivially homomorphic, 1 to 1 and onto, which is isomorphism. Now this by definition. Now theta 2 of A is being defined by minus A. Then we check out whether this is homomorphic. Theta 2 of A plus B is equal to minus A plus B, which is equal to minus A plus minus B, which is theta of A plus theta of B. This is homomorphic, it preserves composition. Now, to check out 1 to 1, theta 2 of A, let theta of 2 of A be equal to theta of 2 of B. This implies minus A is equal to minus B, which will certainly imply A equal to B. Now, to check out the ontoness, we check theta 2 inverse of minus A is equal to theta 2 inverse of minus B, the inverse, which will give us A equal to B, which implies minus A equal to minus B. So because of this isomorphism between n and minus n, between subsets of n to set of integers, the properties of the set of integers will be inherent properties of set of natural numbers. Some properties of the set of integers will, by restriction, stands as properties of set of integers. Even though we don't have the equivalent classes and the equivalence relation, but still they are forming equivalent class. That's why they are not equivalent relation, but they are forming equivalent classes by the restriction. For example, to partition set of natural numbers including 0, we want to partition it into 5 equivalent classes. We use modulo 5. We have 0 class, 1 class, 2 class, 3 class, 4 class. And this is nothing but a minus 0 over 5, a minus 1 over 5, a minus 2 over 5, a minus 3 over 5, a minus 4 over 5. Now 0 will belong to the class of 0, 1 will belong to the class of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and down the line. Again, we can decide to partition 1 over by taking the inverse of each. Having said that, we take this theorem, theorem 1. A is strictly related to B if and only if equivalent class of A equal to equivalent class of B. Now, by definition, equivalent class of A means collection of any x so that x is strictly related to A. It can be also y so that y is strictly related to A. It can be omega so that omega is strictly related to A. Equivalent class of B is maybe y so that y is related to B, maybe omega so that omega is a collection of all elements that are related to B. Now, if A is related to B, and let x belong to the equivalent class of A, this means x is related to A. By symmetry, this x is related to A and A is related to B. By transitivity, x is related to B, meaning that x belongs to equivalent class of B. From equation 1 and 2, equation 1 and 2 implies that equivalent class of A is a subset of equivalent class of B. Equation 3. Now, if you check out, let x belong to equivalent class of B, keeping the fact that A is related to B. This means x is related to B and A is related to B, which means x is related to B and B is related to A by symmetry. By transitivity, this means x is related to A, meaning that x belongs to equivalent class of A. That is, equivalent class of B is a subset of equivalent class of A. This is 4. From 3 and 4, it means equivalent class of A is nothing but equivalent class of B. Another theorem, which we call theorem 2, is the reverse. If equivalent class of A equal to equivalent class of B, it implies A is related to B. Proof. If equivalent class of A equal to equivalent class of B, it means x is related to A and x is related to B. By symmetry, A is related to x and x is related to B. By transitivity, A is related to B, and that's the easy proof. Now, if you combine theorem 1 and 2, we get the necessity, which is the requirement, and the sufficiency, which is the adequacy. Our fourth theorem is equivalent class of A is equal to equivalent class of B, or equivalent class of A intersection equivalent class of B is empty. Proof. Now, two items are either related or they are not related. If they are related, from theorem 3, 2, and 1, equivalent class of A equal to equivalent class of B. This is what we want to show, our goal. Let's assume this. A is not related to B by way of contradiction, and A intersection B is empty. It's not empty as a contradiction. Reductio ad absurdum. This means there is a C that belongs to equivalent class of A intersection equivalent class of B, meaning that C belongs to equivalent class of A and C belongs to equivalent class of B, meaning that C is related to A and C is related to B, which means by symmetry A is related to C and C is related to B. This implies by transitivity A is related to B. So equivalent classes are either equal or they are disjoint. Now functions. Functions y equal to f of x. For every unique x, there is a unique y, X in the domain, there is a unique Y in the codomain. If the domain is A, the codomain may be Y, may be B. Which means our relation, that box, we say A is connected to B, can be written as A, B or A, B. Now, if another connection, C is connected to D, we can join the two to have A connected to B, C connected to D. Now, for mapping, which means it's a relation between two sets in which all the elements of two sets A and B, in which all the elements of A are involved in the relationship, and all two elements of B have one free image. So, for the set A, B, A cross A equal to A squared, which is the set of these ordered pairs AA, AB, BA, and BB. Now, the set of mappings are AB, 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 AA, AB, BA, BB. For two elements, the number of mappings that two elements will generate, two elements of a set will generate, will certainly be 2 to the power 2, which is 4. For nth number of elements is n to the power n equal to 4. Equal to, that's the order of the number of elements in the mapping. For functions, these are the functions. We say for every unique x in the codomain B, there is a unique element in the domain. This is the domain, this is the codomain. Because this simply means set A contains AB and set maybe B contains AB or set A as well set. These are the collection of the functions, but cumulating them together, eclecticing them together, you get the collection of mappings of A squared. Now we have types of functions also form an algebraic field. In fact, that was the reason in 1830 Eberes Galois introduced group, because most continuous functions forms a group. So f of x plus or minus g of x is equal to g of g plus or minus f plus or minus g of x, something like preserving composition. So also f of g of x is nothing but f of x over g of x and down the line. Now, to check oneness, we try if f of a equal to f of b implies a equal to b, the function is 1-to-1. If f inverse of a equal to f inverse of b implies a is equal to b is onto, if a function is 1-to-1. And this, the converse, contrapositive of it is a is not equal to b will implies f of a is not equal to f of b. So do this. A is not equal to b will imply f inverse of a is not equal to f inverse of b. These two are alternative. This is an alternative definition of ontoness, and this an alternative definition of 1-to-1. For example, real line, the linear equation, which means f of x is equal to mx plus c. Now, to check out that this linear equation is certainly 1-to-1 is to check f of a equal to f of b and get the fact that a equal to b. And this is m of A plus C equal to m of B plus C. By cancellation property, this will go. You have MA equal to MB, which implies A equal to B. So also, the ontoness is F inverse of MA plus C equal to F inverse of MB plus C. And this is nothing but A is equal to B, which implies MA equal to MB, which implies MA plus C equal to MB plus C. Now we introduce sequence. Now a function, a real valued function is being defined by I subset of R implies maybe J subset of R. This is a real valued function. Interval is always a subset of the real line. And mostly the intervals, the number of elements in any interval, no matter how small, is not countable. So if this is a real valued function, a complex valued function is defined this way. A natural valued function is defined this. This can be multivariate, but this is always single value because it's on the x-axis. Now, a sequence is the countable. No matter how small is an interval in the real line, it's not countable by Cantor diagonalization method. But we can have a countable infinite subset of the real line being defined in this form. So f of n, this is real sequence. These are complex valued sequence. If C belongs to C and n belongs to n, R belongs to R, and n belongs to R, this may be defined as Rn, and this may be defined as Cn. Though we may use sometimes An or Xn to mean X belongs to R and N belongs to set of natural numbers. Now I want to define increasing, decreasing sequence. A sequence is said to be increasing if xn is less than or equal to xn plus 1. It's decreasing if xn is greater than or equal to xn plus 1. If xn equal to xn plus 1 is a constant sequence. Now if xn is less than xn plus 1, this is strictly increasing, and xn is greater than xn plus 1 is strictly increasing. This is called strictly monotone. Now this is called monotone. Now even the monotone is carrying equality. That means a constant sequence is a spatial monotone sequence. Now for those using x1 is less than x2, which means x1 minus x2 is less than 0, Bible said by maybe if this is f of x1, f of x2, this will be x1 minus s2. This is f prime of x1. Limit as x1 tends to s. That means if f prime of x1 is less than or equal to 0, it's increasing or decreasing. But this is sequence, not functions. Now, a sequence can be bounded. It can be bounded from above. This is an inherent property of this set, the Cantorian set. This set 1, 2, 3 is bounded from above by 3 and has list of the upper bounds 3. Now it's bounded from below by 1 and it has greatest of the lower bound 1. It has least of the upper bound 3. So if there exists an m belonging to a set of real numbers such that xn is less than or equal to m, for all n set of natural numbers, then this sequence is bounded from above. If m is less than or equal to xn, is bounded from below. Now, to combine these two, we have maybe minus m is less than or equal to xn, less than or equal to m. If you combine the two over the real line, this is m. Now, if it is a complex function, this will actually be a cycle. But this is a real valued function defined on the real line. Now we look at convergence. Convergence of sequence. As sequence grows, sometimes it may be reducing to a certain number. This will certainly be 1 over n, no matter how large, or infinity, which is 0. So this converges to 0. And this can easily be demonstrated using a box. Half of the box, 1/4 I mean, 1/4 of the box, 1/8. Finally, the answer will be 1. So convergence is similar to boundedness. Every convergence sequence is bounded, but not every bounded sequence converges. So a sequence xn is said to be convergent if given epsilon greater than 0, there exists a delta greater than 0, such that xn minus L is less than epsilon whenever 0 is less than x minus x0 is less than delta. This is convergence of a function. We now translate this convergence to convergence of a sequence xn. This will be xn, but we'll be dealing with infinite sequences, meaning that this x0 will be infinity, meaning that, but we are dealing with countable subset of the real line. This x will now be n, meaning that n is not too far different from infinity. That's why we use for all n bigger than or equal to n, where this n is no matter how large, meaning that instead of delta greater than 0, we use n is bigger than no matter how large, belonging to set of natural numbers, and depending on epsilon, some texts use n epsilon. Now, this is gleefully okay, except for divergence when a also belongs to set of natural numbers and n is no matter how large. Thus, we have to go with n greater than or equal to n, something like for all n and for all this, only that we don't use this to mean that the limit as n tends to infinity of xn is nothing but infinity. It can be plus or minus, plus or minus. So we take examples. 2 over n, limit as n tends to infinity, prove that this is 0. Now, if we use the definition, we say 2 over n minus 0 is less than epsilon, and look for all n bigger than or equal to n. Or we can use this to get this. Now this, since n is positive, this is less than epsilon, meaning that 2 over epsilon is less than n. Meaning that 2 over, meaning since n is a very large number and epsilon is a very small number, epsilon and delta belongs to the interval 0 and 1, meaning that the delta and epsilon are members of this interval 0 and 1. They take infinitely many different kind of numbers. That means they are variables, not they are varying, not specific numbers. So do infinity. So the proportion is inverse, and also n is inversely proportional to delta. 2 divided by a very small number is a very large number, call it n, meaning that n is less than n, meaning that n is bigger than n, meaning that n is bigger than or equal to n, meaning that for all n, is bigger than or equal to n as required. And this applies to 3 over n limit equal to 0, 4 over n equal to 0, 5 over n equal to 0, and down the line. And this is why we call this mathematics abstract, because once you solve one particular example, you have solved so many others. Now, limit as n tends to infinity of 1 over 2n also is 0. Also, by definition of this of convergence, we use less than epsilon. If this is 8, we use 8. But since it is 0, we use 0. Meaning that 1 over 2n, since n is positive, is less than epsilon. 1 over 2 epsilon is less than n. This is also reciprocal of epsilon, meaning it's a large number. Call it n. N is less than n, meaning that n is bigger than n, meaning that for all n is bigger than or equal to n. And this also has solved so many functions: 1 over 3n, 1 over 4n, 1 over n squared, and down the line. We take a special function limit as n tends to infinity of 2 all over 1 plus p to power 3n. If you make an expansion of this, what you get is 1 plus p squared plus p cubed, 3, meaning that 1 plus p to power 3 is greater than 1 plus 3p. Now if you keep multiplying 1 plus p to power 3 greater than 1 plus 3p, multiply, what you get is 1 plus p to power 3 n times is greater than 1 plus 3 np. And that means the converse will be less than epsilon, because n and p are all positive numbers. Now to make n the subject here, we take 1 is equal to epsilon into 1 plus 3 np. This is 1 equal to epsilon plus 3 np epsilon. And this is 1 minus epsilon all over 3p epsilon is equal to n. Now 1 minus epsilon is 0 point something. A small number times a positive number, a small number times 3. We can call this n. That means n. I think we are using less than, strictly less than, we inherited from here. So this is strictly less than n, meaning that this for all. Now we take some theorems. Every convergence sequence is bounded. Convergence implies boundedness. Proof. Every convergence sequence is bounded, but not every bounded sequence converges. A sequence is said to be convergent if this happens. By a property of absolute value called triangular inequality, this is xn minus l, meaning that xn minus l is less than epsilon, which means xn is less than l plus epsilon. Call this m, but to avoid suspicion and doubt, since sequences are countable, we take xn minus 1 up to xn, pick the maximum, call it m. Since n is bigger than or equal to n, this will certainly be n, and this will take l plus epsilon. Now we introduce xn, a sequence xn converges to one particular limit. One sequence cannot be converging to two different limits. Now that's the theorem. We look at the proof. Let, by way of contradiction, xn converges to two different limits. Now we check out the difference between L1 and L2, whether is that significant. L1 minus L2 is nothing but L1 minus xn plus xn minus L2. And this is less than or equal to, from triangular inequality, L1 minus xn plus xn minus L2, which, because a property of absolute value, is xn minus L1 plus xn minus L2. If this is half epsilon, then this will be epsilon by 2 plus epsilon by 2, which will give us epsilon. What that means is absolute value of x1 minus s2 is strictly less than epsilon, which means, because it's strictly less than, which means the difference between the two limits is insignificant, or we say the number that is strictly less than epsilon is 0, meaning that L1 minus L2 is 0, which means L1 minus L2 equal to 0, when L1 is equal to L2. Now a subsequence, we introduce a subsequence. If we have a set 1, 2, 3, 4, 5, 6, now this is a subsequence of that. That's addition of this. If this is n plus 1 is a subsequence, n plus 2 is also a subsequence of n, and down the line, n plus n. Now if we check out also 2n, this will give us 2, 4, 6, 8, and down the line. If we check 3n, this will give us 3, 6, 9, down the, each is a subsequence of this. That means if we have xn, then xn plus 1 is a subsequence of this, and x2n is a subsequence of this. But in order not to conflict the argument of saying xn and xn plus 1 is the next term after xn, or sorry, not to complete it with this, we go for xnk. This is called a subsequence. So we want to check out now that a subsequence converges to the limit point of the supersequence, which is a theorem. If a sequence converges to L, then its subsequence xnk will converge to L. Now this means xn minus L is less than epsilon for all n bigger than or equal to n, and this means now we check whether this can give birth to the convergence of xn, but every Cauchy sequence converges for all n m bigger than or equal to n. Since every Cauchy sequence converges, it means xn minus xnk is less than epsilon for all n m bigger than or equal to n. Summing up the two, we get, or subtracting 1 from 2 or 2 from 1, what we get is xn minus L minus xn minus xnk is less than epsilon minus epsilon, which will give us 0, which is less than epsilon. And from triangular inequality, this is xn minus L minus xn plus xnk is less than epsilon, this epsilon. This will go, we have xnk minus L is less than epsilon. So a subsequent converges to the model sequence. Now every sequence has a monotone subsequence. We have seen the case that the constant sequence is a spatial subsequence, and each is depending on an increasing sequence n. This by definition n. Since n is increasing and x depends on n, then every sequence has a monotone, which means increasing or decreasing subsequence. Because even the constant sequence is a special case of the monotone sequence, not strictly monotone sequence. So we check out the Bolzano-Weierstrass theorem. First, before we check out Cauchy sequence. By definition, xm minus sm less than epsilon for all n bigger than or equal to n. Now, the theorem under Cauchy theorem is saying every Cauchy sequence converges. This is a bi-way, a two-way convergence. Every Cauchy sequence first is bounded, meaning that xn minus xm is less than epsilon. By triangular inequality, this is xn minus xm. Now this is xn is less than xm plus epsilon. As we have seen earlier, this we call it m. But to clear it out, we say the maximum of x1, x2 up to xn. xn minus 1, xn is less than this, so we replace it. Sm minus 1 we replace by capital N. Now the Bolzano-Weierstrass theorem is every infinite bounded sequence converges. Every infinite and bounded sequence has a monotone subsequence, and the monotone subsequence is either increasing or decreasing and is bounded, so certainly it converges. Now a corollary to Bolzano-Weierstrass theorem is every infinite and bounded sequence has a convergent subsequence. Every infinite bounded has a convergent subsequence. Because the modal sequence converges, the subsequent will certainly converge to the limit point of the supersequence. That's from the fact that every Cauchy sequence is bounded. So now we check out some sequences may be bounded but may not converge. For example, minus 1 to power n. If you check out this minus 1, 1, minus 1, 1, minus 1, 1. If you check out the series, it will give minus 1 or 0. So this certainly converge, but this is called the limit inferior of the sequence, and 1 is called the limit superior, because by controlling set theory, this is this. So limit inferior of this set is minus 1, and limit superior is 1. Now we want to prove that set of natural numbers diverges. Now, keeping the fact that x is greater than or equal to n, and set of natural numbers is nothing but n, where n belongs to n, like a vicious cycle, meaning that set of natural numbers is nothing but n, and n is bigger than or equal to n. Now, suppose from trichotomy, three things will happen. Either n is less than a, or greater than a, or equal to a. So, if n is less than a, if n is greater than a, then it means n is bigger than or equal to a, meaning that xn, which is a natural sequence, is bigger than or equal to a for all n bigger than or equal to n, the divergence. If n is equal to a also, that means n is bigger than or equal to a, meaning that xn is bigger than or equal to a. Now, n and a are no matter how large. Even if n is less than a, still n is bigger than or equal to a, because n and a are arbitrary. So if n is greater than or equal to n, arbitrary number no matter how large, then it's greater than a. So the next thing is to look at series. If xn is a sequence, then summation of xn is a series. But since we'll be dealing with infinite sequence, which means n from 1 to infinity, since the sequence is infinite, the series will certainly be infinite. But we can study a partial sum, n from maybe 1 to n of xn, or I running from 1 to n, to have a vicious cycle. If this converges, this converges. If this converges, by comparison test, this converges. So we take the limit as n tends to infinity of this, which is the sequence. This partial sum is called xn. So we take our well-known geometric series to see its convergence. Summation of Rk, k running from 1 to infinity. Now to check the convergence of this, we check the convergence of k from 1 to n of Rk. Call it xn. Now xn is equal to, we can check 0 to minus 1 to mean R0, R1, R2, up to Rn minus 1, n number of terms. If we start with 1, we end with this. Now R times xn is nothing but R plus R squared plus R cubed plus R to the power n. If you subtract Sn minus Rsn, what you want to get is a term before this is 1 minus R to the power n. You can factor out Sn to have xn into 1 minus R is equal to 1 minus R to the power n. Dividing both sides by 1 minus R yields the result. Now, we have to take the limit as n tends to infinity to get the convergence of this. So the limit of xn, limit of Sn as n tends to infinity is limit n tends to infinity of 1 minus Rn all over 1 minus R, which is equal to limit as n tends to infinity of 1 over 1 minus R minus Rn all over 1 minus R. Now if n is a small number, say 1 over k, between 0 and 1, R belongs to 0 and 1, then R will be something like 1 over n, which if you put 1 over n, it will be 1 over kn, meaning that this Rn is nothing but kn, As n tends to infinity, this will be k to the power infinity, which is 1 over 0, or a number divided by 0 divided by infinity, which gives 0. And this is independent of n, so we get 1 minus r. Now if r is positive, r is bigger than 0, we get divergence. If r equal to 1, then it's undefined. This is 1. If r is equal to 1, this is 1 over 1, which is 1 over 0, which is undefined. Now we check also a special series 2 over n plus 1, which by partial fraction is nothing but summation. N running from 1 to maybe infinity, n running from 1 to infinity is nothing but 2 over n plus, or maybe minus 2 over n plus 1. This is from the fact that 2n plus 1 is nothing but a over n plus b over n plus 1. Crossing, this is a in n plus 1 plus b into n. If n is 0, this is a equal to 2. If n is minus 1, this is minus b equal to 2, meaning that b equal to minus 2. So this is correct. Now, this is Sn, limit as n tends to infinity. So our Sn is summation n from 1 to infinity of 2 over n minus 2 over n plus 1, which is equal to 2 over 1 minus 2 over 2 plus 2 over 2 minus 2 over 3 plus 2 over 3 minus 2 over 4 plus 2 over n minus 1 minus 2 over n plus 2 over n minus 2 over n plus 1. Now this will go with this will go. So what you get is 2 minus 2 over n plus 1. Now take the limit as n tends to infinity of this, which is the limit as n tends to infinity of Sn. This gives 2 minus 2 over infinity, which is 2 minus 0, which is 2. Now, to check out convergence of series, a necessary condition, what is required is if the sequence converges to 0. If xn equal to a squared, a cubed, up to an minus 1, and Sn minus 1 to be up to Sn, this is a plus a squared plus a cubed plus an minus 1. Now, to prove that summation of n runs from 1 to infinity converges is to check whether this Sn converges to 0, meaning that limit as n tends to infinity of an is 0. Now if you subtract, this is Sn minus 1 is equal to 0. This, what will be remaining, because there's an minus 1 here, we subtract this, we have an. This is the series. This difference between partial sums. So we take limit as n tends to infinity of this, limit as n tends to infinity of this. Now, this is limit of Sn minus limit of Sn minus 1. A subsequent converges to the limit point of the supersequence. If the limit point of the supersequence is L, the limit of the subsequence is L, which gives 0, meaning that this 0 is limit of this, limit as n tends to infinity of an. Now, if summation of an converges, if absolute value of an converges, the summation of an is said to be absolutely convergent. But if this doesn't converge, it's said to be conditionally convergent. Now, if summation of an converges, then summation of an will converge, because this summation is less than the summation of an. And this converges means it's less than epsilon, because this is like minus 0 less than epsilon for all n bigger than or equal to n, meaning that this summation of an is less than epsilon, this property of absolute value. And this means summation of an minus 0 is less than epsilon for all n bigger than or equal to n, which is convergence of this, because this is nothing but summation of an, which is the limit of this as n tends to infinity is 0. Now we check out Cauchy general principle of convergence. This one of series. It said if the partial sum Sm minus Sm is Cauchy, then the series summation of an converges. Now, if the partial sum converges, Sm converges to Sm, then it means summation of n from 1 to n converges. And after taking the limit as n tends to infinity, this converges. Now, if this converges, by comparison test, it means even summation of I running from 1 to n of ai converges. And this converges, meaning summation of ai 1 to m also converges. This is called Sm, this is called Sn. So, since this converges, these two converges, and we find the difference between convergence sequence, we get 0, which is less than epsilon. Because this minus this is this, which is less than epsilon. Now, we check out Sandwich theorem. Of sequence. If 0 is less than or equal to x and less than or equal to yn, and yn converges to 0, then xn will converge to 0. And the proof is xn is certainly less than yn. But yn tends to 0, this is yn minus 0 is less than epsilon, meaning that xn is less than epsilon, meaning that xn minus 0 is less than epsilon, which means xn converges to 0. Then we have a corollary to Sandwich theorem. Corollary of the Sandwich theorem, we said if xn is less than or equal to yn, less than or equal to zn, and zn converges to a, xn converges to a, then yn will certainly converge to a. The proof. Now, subtracting xn all through, we have xn minus xn is less than or equal to yn minus xn, less than or equal to zm minus xn, meaning that 0 is less than or equal to yn minus xn, less than or equal to zm minus xn. Now, if you take the limit of this, limit of zn minus xn, this is limit of zn minus limit of xn, but the limit of zxn is a, the limit of zn is a, this is 0. So since this converges to 0, by Sandwich theorem, this will also converge to 0, meaning that limit of yn minus limit of xn is equal to 0, meaning that limit of yn is equal to limit of xn. But the limit of xn is a, so certainly the limit of yn will be a. So the next thing is to check comparison test. Comparison test. If you have summation of 1 over 5n, or maybe 5n minus 1, if this series n running from 1 to infinity is less than or equal to 1 over 5n, which is equal to summation of 1 over 5 to the power n. Now since this converges, because this is 1 over 5n less than epsilon, which is, you can call this, now this is 1 over epsilon is less than 5 to the power n, take log, this is log of minus log of this, all over log 5 is less than n, the minus log base 5 of epsilon less than n, call this n. So the for all n bigger than or equal to n certainly exists. And this means 1 over 5 to the power n plus 2 will converge. 1 over 5 to the power n minus 10 will converge, and down the line. Now look at ratio tests. Ratio test is saying if an plus 1 over an, the limit as n tends to infinity is bigger than 1, is divergence. If less than 1, convergence. If it equal to 1, is undefined. And we take an example of maybe 2 over n. If this is an, then an plus 1 will be 2 over n plus 1. An plus 1 over an will be 2 over n plus 1 over 2 over n. This will go, you have n over n plus 1. Take limit of n plus 1 as n tends to infinity. This will give us 1 over 1 plus 1 over n, limit as n tends to infinity, which is 1. That this converges by ratio test. If you try 3 over n, 4 over n, and down the line will also certainly converge by comparison test.